We also want our basis function to be sparse in the sense that sparse grids are sparse, meaning we want to limit the mixed order of a given basis function, and we want the support of a given basis function, of all the basis functions, to be of some limited topological dimension, i.e. we only want to represent ones up to, say, being on a tetrahedron, rather than representing the ones that have a support of higher dimension than that. So, for instance, this sort of relates sparse grids to serendipity elements, in which you do exactly that. You limit yourself to edge and, say, low order phase unknowns in the 2D case. So, to mesh with this, for different problems we can do different things. For instance, for standard 2D, 3D meshes, we can have our spatial mesh crossed with whatever extra dimensions we want. For instance, if we're doing radiation transport, we can have our domain crossed with, say, a discretization of the angles. However, for the quantum mechanical problems, we want to mesh in line with the features of our problem. And this is where we get to our very simple example meshes, which is where we have nested simplices, wherein an initial simplex is glued to a larger simplex by what I like to call a hyperprism, wherein you take a cell of dim -1 across the interval and just expand it out to the next facet. And so this allows us to easily extend a given mesh to n dimensions with simply order n cells. So we've also, because we're doing problems that the solutions must necessarily exponentially die, we can very easily derive a difference equation that'll give us an optimal spacing for this mesh. And this is done by looking at the error at the midpoint of a cell. So if we space the midpoints of the cells like this and project the exponential into 2 to 9 dimensions, we see that for the first order case, meaning we only have, we essentially use the barycentric coordinates as basis functions, we get reasonably bad blow up in our error, neglecting the fact that the overall area also blows up. But if we use the second order, we get a reasonable approximation. It almost grows linearly for a long time. And so, since we want to start at 3 and 6 dimensions, we thought this was a good starting point. So we want to solve the hydrogen atom, which is just, that should be a delta, but yeah, 1/2. It's the Schrodinger equation with just 1 over r term as the potential. And we know the exact energies and we know the exact solutions. So if we look at this and we look at different polynomial orders we use for the facet, we see that we get reasonable geometric convergence to the actual energy we want. And we're also able to recover more and more higher parts of the spectrum. So for instance, here's the ground state. Here is going to be the 2s state, and here's going to be the 2p state. But these, of course, should all have the same energy, which we eventually see that they converge to. We also can look at the radial error, and if we look at the red line, we note that it has a definite peak in where we have error. This can be related to the aspect ratio of the cells given our very simple mesh framework. And it's obvious that if we were to implement some immediate or some very simple adaptivity for this, we can bring this far down. For instance, we still have this kind of problem at 5th order, but it's much, much lower. So if we were to just refine there, it would be very good for this. So the missing pieces are therefore adaptivity, high-dimensional quadrature, and meshing for n electrons. So first I'll describe our problems with adaptivity. We don't want to refine the mesh in n dimensions. That would be incredibly messy. Although there is a very simple topological way of refining a prism mesh into simplices. It's just not something we want to do in 3n dimensions because it would give us exponential blow-up. So we have a way of a priori doing radial refinement, but we want a notion of a priori angular refinement, and one way to do this would be the aspect ratios. We also want an a posteriori anisotropic estimate and P refinement. The other major issue here is quadrature. Because we have this potential function, we need to be able to tie our basis functions to the potential function, and therefore we can't just do a pure spectral method like we would want to do, for instance, by using Rob's Bernstein polynomial methods. So if we do just the simplest thing with quadrature, we get something like this, but we get a relatively small number of points, but that is at order S. If we do the pinched hypercube rule, the standard coordinate warping, we get S to the n, but we get, that's order 2s plus 1. Whereas if we look at these classes of rules that are typified by the Müller-Grundmann rules, and they're combinatorially derived and barycentrically symmetric, we get around the same order as the uniform rules, but it's a 2s plus 1 order. And these can easily be expanded into as many dimensions as we want. For a reasonable order, they're still relatively small. Another way we could look is to assemble, say, the Laplacian part of our problem spectrally, and then to do some low discrepancy sequence rule, such as, well, the Monte Carlo community has tons of these things. And that would give us a bounded error based upon the number of points. Another option here is to do an adaptive lattice rule, wherein we continue to refine another type of low discrepancy sequence where you go over a lattice, but we can refine it such that we can match the potential better. So one major problem with meshing in this many dimensions is handling the potential function costs. We have these singular surfaces. For instance, in helium, which this is, we have where the first electron is at the nucleus, the second electron is at the nucleus. And those are both three-dimensional spaces. We also have where the first and second electron are at the same point. That's also a three-dimensional space, and they only intersect at one point where they're all at the origin. So to do this, to match the configurations, to match this in full 6D is a little bit difficult. We seem to be able to rotate the simplex so we can do this. But to do this whole problem, we have to do something much more adaptive and much more clever than just the simplex, it seems. So we have a couple possibilities. One is sort of an expanding Cartesian mesh, which would give us 2 to the dim cells, but would easily be matchable to these surfaces. We could cross our mesh for hydrogen with another one of our meshes for hydrogen, which would not have very good complexity, but would probably work for this problem. We could do the 6 simplex, or we could do what I like to call a lens space mesh, wherein we take some lower dimensional facet, like say the surface where the electrons are at the same point, and then surround it by some 5D simplex and connect it into cells which then conform to the potential surfaces. So here's what we sort of learned from this project so far: how to engineer a general mesh framework, how to create function spaces for n-dimensional systems. But really, discretizing configuration space for quantum mechanics systems is still very difficult, and I think it's going to take a lot more work in any framework, sparse grids or something like this, to get it really working. We're looking for better apps. For instance, radiation transport would be a nice place to look. And that's pretty much it. Thank you.